Hello, everybody. My name is Jose Carrillo. I'm one of the organizers of this first online Congress of the IAHR. We are going to start right now the fluid hydraulic session. To do this, we are going to have two chairs. We are going to have Michael Nons and Angelo Leopoldi. Please, I think that right now the best option is that you introduce your technical committee, and later we move to the presentation. For the presentations, the participants need to show your poster, and you will have between 3 and 5 minutes to do the presentation. And later, we will have a coffee break to try to solve some doubts, some questions, and to explain a few things regarding your specific works. Okay, so please, Angelo, Michael, you can start.
Okay, thank you. I'm very happy to welcome you on behalf of the IAHR Fluvial Hydraulics Committee. Fluvial Hydraulics Committee is one of the oldest technical committee in IAHR, since the fluvial hydraulic is a traditional research topic in the hydraulics research. As you know, the physical processes in rivers are determined by the interaction between water and sediments. So water flow and sediment transport are the traditional topics of study of this branch. However, since the chemical and biological processes are becoming more important, especially as their relationship to river morphology, consequently, the Fluvial Hydraulics Committee is now interested in research that involves components from other disciplines like biology, geomorphology, soil mechanics, and oceanography. The fluvial hydraulics, in my opinion, needs contact with practice. So the researchers depend on the engineers involved in practical river management. As well, the models and scientific approach require data and experience from the field. But on the other hand, the engineers doing practical work can benefit from research results and innovation by applying them in practice. The Fluvial Hydraulics Committee organized a biennial congress, the River Flow. Our 11th edition will be in Kingston, Ontario next year. River Flow is the natural place for exchanging ideas and experience in our research topics. I encourage you to join our committee also during our meetings. Meetings are usually organized during the IAHR Congress and the River Flow Congress, but we are thinking also about the possibility of more meetings using the online platform. So I thank you for your participation in this session, and now I hope we can start with our first presenter. If the program is correct, our first presenter is Roy Dirks, and the paper's title is Modeling Erosion of Pre-embankment Bridges in Covers and Ridges in the eastern floodplain due to major flood events. So please, Roy.
Yes, hello. Do I have to present my second screen? Or let's see. How do this? Oh, this is not working correctly. Share screen. share. Come on. Okay, are you seeing my screen now?
Yes, perfect.
Okay. Hello, all. I'm Roy Dirks from the Netherlands. I want to thank you for attending my presentation. The first of many today and tomorrow. The title of my research is Modeling Erosion of Pre-Embankment Breaches in Cover sand ridges in the IJssel floodplain due to major flood events in medieval times. This title raises some questions at first. That's why I want to start with some background. Cover sand ridges, what are those? Cover sand ridges are natural elevated areas that formed in the last part of the glacial period due to wind transport. And these created a watershed between the Rhine floodplain and the IJssel floodplain. We've got the Rhine floodplain over here, with the Rhine flowing from Germany, this is Andernach, through the Netherlands and discharging to the west and to the north. Currently, the IJssel is laying over here and has formed, but 1500 years ago, the IJssel wasn't formed yet. And from geological mapping and data, has found that in the medieval times, 2 breaches have formed in those cover sand ridges. And they are probably related to some extreme flood events that have occurred in that time period. Well, what happened? A large flood event happened and breached through the cover sand ridges here and formed 2 breaches, the westerly and the easterly breach, referred as the westerly and the easterly breach. Where one breach expanded, the easterly breach, and became part of the River IJssel, the westerly breach eventually silted. And we wanted to know, why did the one silt up where the other one expanded and became part of the river, and which flood waves could have formed these breaches in the cover sand ridges. Therefore, we constructed a floodplain of the time period before the River IJssel existed, and we set up several hydrodynamic models of the floodplain with 2 small breaches with different depth and width in the westerly breach and in the easterly breach, different width from 50 meters to 100 meters and different depths from 1 to 2 and 4 meters depth. With these various breaches, we try to replicate the breach development in time with different stages through the breach, from small to large. And with these models, we can compare the hydrodynamic conditions in both breaches. And from the hydrodynamic model we have set up using the reconstructed floodplain and the flood waves, we could use the hydrodynamic data in the breaches to set up a erosion model and a sediment transport model. And from these models, we could easily find that the westerly breach suffers much less erosion velocities and sediment transport, has a lot less sediment transport capacity than the easterly breach for each scenario. So through time, the easterly breach always was expanding faster in time than the westerly breach. And from that, we can conclude that the easterly breach this was had a more favorable conditions to expand than the westerly breach. But now I think you have got all one question. Why do we want to know this? Well, we have from an archaeological historical perspective, it is interesting to know how the River IJssel has formed. If we can replicate the formation of this river, it gives us insight in why the Netherlands looks like it as it does today. And besides that, it can offer opportunities relating to other river formations in other countries all over the world. And besides this, from a water engineering perspective, it is interesting because if we can quantify major historical floods with a large certainty, so if we know which floods have formed these breaches, we can add this to the discharge data that's currently available. Only 100 years of data is available now. And with a larger data set with much more floods and large floods, extreme floods, This gives more certainty for future design projects and safety assessments of hydraulic structures and or building with nature projects, etc. And that's why it's important. This was it, my short presentation. Stop sharing. How do we do that?
Okay. Sure.
Okay, thank you, Roy. Our next presenter is Eduardo Bestune, and his presentation is data-driven modeling of high-flow related poor water quality events in the Mid-Brisbane River. Thank you, Eduardo.
Thank you, Angelo, for the introduction, and thank you, everyone, to all the participants all around the world to be connected now and following these presentations. So I'm a lecturer at Griffith University in Australia, next to Brisbane, and this is a project that I'm presenting, which is part of a 3-year collaboration with SAQ Water, which is the main bulk water supplier in Southeast Queensland, here in Australia. And the focus of this particular project is here in this location here in the map. That's the Mount Crosby water treatment plant. And it provides drinking water for the entire Brisbane city and for other regions as well. So it's a very large and important treatment plant in this region. And it draws water from the Mid-Brisbane River, which is here, as you can see in the map. The Mid-Brisbane River has a number of water quality issues every time we have some high flow events, although this really depends on where the rainfall falls, because there are just a number of small creeks which really contribute a lot to issues such as turbidity and conductivity, which then flows down to Mount Crosby. On the good side, we also have Wivenhoe Dam that you see here, which also flows into the Mid-Brisbane River. Wivenhoe Dam usually has a better water quality and can be used for dilution if the timing is right to help reducing water quality issues at the treatment plant downstream. Wivenhoe Dam was also the dam that spilled during the 2011 Brisbane flood events. So after that, a lot of work has been done from a modeling point of view, but usually there were always process-based models to look at hydraulics and hydrology of the catchment, but not much has been done from a water quality point of view to help the operators of the treatment plant to adjust water treatment based on these sudden water quality variations. So the focus of this project is to apply a data-driven modeling approach and try to predict a bit in advance, up to 1 or 2 days in advance, poor water quality events, conductivity, turbidity, and also flow. So we're gonna predict also water flows as well at different locations. How are we gonna do that? Well, all these other colored dots that you see along the river, these are high frequency water quality monitoring stations that have been installed in the last 5 to 7 years. And they collect data every 10 minutes to 1 hour. So we have a lot of data that we can use, and we did use already with our machine learning approaches to try to build these models that I talked about. So up to this point, we are more or less halfway through the project. We already developed flow prediction model, which is relatively accurate, and we developed a little user interface that you see here. So we can predict the timing, and so both the lag time and the peak flow value at downstream locations based on data that we have upstream. And we started looking also at the water quality, and we found meaningful, like high correlations as well between turbidity and conductivity at different locations. So we are hopeful that we can finalize this part of the model soon. The last piece of the puzzle would be to look at rainfall, like historical rainfall data as well for different stations in the catchment, to try to link this component as well. If we can do that, then the final product will be a decision support tool for the water treatment operators, which based on weather forecast, based on rainfall forecast that we can access in real time, we can then provide an early warning to the operators in case we predict a poor water quality event coming in the next few hours or so. So we're hopeful we can achieve that in the next year or so, and that's it for me. Thank you.
Thank you, Eduardo. And
Let's stop sharing.
we're almost in time. Our next presenter is Si-Young Kwon. His paper is Identification of Contaminant Source Using Truncated Breakthrough Curves in Rivers. Please, Si-Young.
Good afternoon. I'm Si-Young Kwon, PhD student studying at National University. My research title is Identification of Contaminant Source using Truncated Breakthrough Curves in Rivers. In this study, we developed contaminant source identification model using contaminant spill scenarios from contaminant transport numerical model and machine learning model using the scenarios as training data set. First of all, the transient solution model was used as a contaminant transport model to simulate the skewed and long-tailed breakthrough curve caused by the storage zone effect. The TSM model used finite differential method and the Crank-Nicolson method to approximate the spatial and temporal derivatives. And the TSM parameters were estimated by using the empirical equation from principal component regression. By using this model, the contaminant space scenarios were generated in Gamkuri, South Korea, as shown in figure 1. And by using this model, the model domain was 39 kilometers with 30 potential spill locations, as shown in figure 1. Next, the machine learning models were compared to select the optimal model for prediction of the spill location and spill mass. The models used for comparison were decision tree, random forest, XGBoost, support vector machine, and ridge regression, as described in table 1. These models use the 21 kinds of whole breakthrough curve features and 8 truncated breakthrough curve features, such as standard deviation, skewness, and rising rim slope, area of rising rim, as like this as input variables. Also, the validation of the proposed models were performed from the 5-port cross validation. We generated scenarios and field tracer dataset. As the result of spill location prediction, all nonlinear models showed accuracy over 90% R-square when the whole breakthrough curve was used as input variables. But the only spot vector machine showed accurate result when truncated breakthrough curves used as input variables. In the case of spill mass prediction, all nonlinear models showed accuracy over 90% R-square when both whole breakthrough curve and truncated breakthrough curve were used as input variables. As a conclusion, the relative importance of each machine learning model show the reason of the aforementioned validation result. The figure about the relative importance of feature is skipped due to the limitation of one-page poster, but the feature importance show that the tree-based model highly depend on the slope of tail, which can be calculated by only a whole breakthrough curve. These models are difficult to predict well with risk contributed truncate breakthrough curve features. In the case of support vector machine, the overall feature importance is more distributed than the tree-based model. Therefore, using only the truncated breakthrough curve features significantly contributed to the prediction. Therefore, the nonlinear support vector machine is the most optimal model for both spill location and spill mass prediction. And thanks for listening to my presentation.
Okay. Thank you, Si-Young. So our next presenter is Rafael Berguillos, and his presentation is about vertical integrated and moment equations for non-hydrostatic flow modeling MATLAB platform. So please, Rafael.
Thank you, Chair, for the presentation. I'm going to present this poster on behalf of my colleague from the University of Córdoba, Pedro Gamero, who for personal reason is not able to do this presentation. As you probably know, the use of non-hydrostatic model is often required to provide realistic prediction in coastal and open channel flows. For that, the use of depth integrated model is a common practice. The main purpose of this work is to present a user-friendly software platform to apply the vertically average moment equation model, also known as PAM model, to simulate some non-hydrostatic coastal and open channel flows. The software is freely available and can be freely downloaded through this link. As you can see in the first figure, the initial window of the software platform allows the user to select between coastal flow and open channel flow applications. The open channel flow applications enable the simulation of fabric waves and flow over Gaussian obstacles, whereas the coastal flow windows allows modeling solitary wave propagation over horizontal beds and solitary wave propagation with run-up. All the applications include numerous editable options to customize the numerical experiment. The second figure shows a couple of applications of the software platform for the cases of flow over a Gaussian obstacle and solitary wave propagation with run-up. The results are compared with experimental measurements and hydrostatic solution obtained with the Sine-Benet's equation. As you can see in the figure, the BAM model provides more realistic prediction for both the bed pressure and free surface distribution in the first test and the free surface values in the second test. In this work by Gamero et al., more detail and application of the software platform are described. The MATLAB script of the BAM model, along with a hydraulic reference manual, are also provided as supplementary material in this paper. The accuracy of the result in all the applications highlights the potential of this software platform to model open channel and coastal flows, where non-hydrostatic pressure and non-uniform velocities shall be accounted for. The model has a wide range of applications, such as the prediction of free surface profiles over bed forms and obstacles, the estimation of wave run-up in coastal areas, or the design of laboratory experiments, among others. Thus, the software platform presented in this poster and the MATLAB scripts provided in this paper are useful tools for teaching, research, and management purposes. Finally, just to mention that this work was funded by the Spanish government through this research project and these two research contracts. This is everything from my side. I'm at your disposal for answering any question, and thank you very much for your attention.
Thank you, Rafael. Also because non-hydrostatic depth integrated model was my first scientific love. By the way, the next presenter is Saroy Karki, and his presentation is a question. How good are 2D morphodynamic models in reproducing bed morphology of meandering channels? A comparative analysis of 3 models. Please, Roy.
Sorry, Angelo.
Okay. It's not
Thank you.
In our presentation. So next presenter is Rossella Belloni. And the presentation is a satellite-based analysis of the geomorphological efficiency of river dunes. Please.
Thank you. I'm sharing the video. Okay. Good morning, everyone. I'm Rossella Belloni, a PhD student of civil engineering at Roma Tre University in Rome. And today I show you a satellite-based analysis of geomorphological efficiency of river plumes. River plumes are turbulent flows generated by river freshwater discharged into coastal waters. River represents the measured link through which sediments are transported up to the coastal waters. Therefore, the assessment of river plume dynamic, which rule the sediment low dispersal into coastal area, is of strong scientific interest and practical importance. Here, we investigate in particular the geomorphological efficiency of Pau River Plume, which is the main Italian river flowing in the northern Adriatic Sea. To this end, a time series of Sentinel-2 images, that is an ESA mission designed to acquire optical imagery over land and coastal waters, was collected and processed. The images were collected for the period June 2015 to April 2018, excluding those images with significant cloud cover and sediment resuspension by wind and wave action, and without any clearly visible river plume. The images selected were later processed using Agolite, that is an automatic processor developed for the atmospheric correction of Sentinel-2 images on coastal and inland waters. The processor allows furthermore the calculation of many satellite-derived parameters, such as turbidity, using in particular the algorithm developed by Togliotti et al. That is a key parameter in sediment transport monitoring and also in water quality monitoring, being a proxy variable of suspended sediment concentration in the water column. The overall coastal area affected by the river plume dispersal was identified in each image, comparing turbidity values with a threshold established considering the background turbidity of the Adriatic Sea. And then the spatiotemporal variability of river plume morphology was captured using a relative frequency map of the turbidity values. River plume morphology were then linked to the main environmental forcings affecting the dispersal in the northern Adriatic Sea, that is wind and river discharge, and to evaluate how they affect the overall pattern of the river plume. In this regard, discharge and wind data refer to a temporal window of 72 hours before the satellite acquisition were considered to take into account that the observed dynamics depend on the evolution of environmental forcings in the antecedent periods. The analysis in particular showed plume morphologies with a moderate spatiotemporal variability and confirmed the major role of wind and river discharge in affecting the overall structure. In particular, long-lasting northerly winds tend to compress plume against the coast, increasing freshwater and sediment transport in the alongshore direction, promoting in this way the geomorphological efficiency of the plume. On the contrary, long-lasting southerly winds determine sediment delivery far offshore, reducing the supply on the surrounding coastal areas. In the end, for what concerns discharge, it seems to limit the influence of winds during high flow events. And in these cases, river plumes tend to exhibit a more prototypical morphology. Thank you for your attention.
Thank you, Rossella. So we are ahead of schedule. And the next presenter is now Diana Pitta, and her presentation is water quality modeling of Paraná River between the Yacyretá Dam and its junction with the Paraguay River. Please, Diana. Your microphone. Diana, you should activate your microphone.
In sanitary engineering. Greetings to all. My name is Diana Pitta.
Okay.
I am from Venezuela. currently living in Buenos Aires. I am a civil engineer, and I'm completing a master's degree in sanitary engineering at University of Buenos Aires, Argentina. I am an active member of YPM Venezuela. I would like to present my work titled Water Quality Modeling of Paraná River between the Yacyretá Dam and its junction with the Paraguay River. The following work shows the results of the study of the dispersion capacity of 6 hypothetical pollutants and the variation of the concentration along a section of the Paraná River between the Yacyretá Dam and the confluence with the Paraguay River, making use of the water quality model in HECRAS software. First, I'm going to describe the methods. Figure 1 here shows the Yacyretá
Diana,
Dam.
please, could you change your image? We are seeing your folder instead of the presentation.
The subject map models from the specialization course, sanitary. Can you hear? Repeat me, please.
We need to see your presentation. You are seeing the folder.
Yes, I put
Please
a record.
Compart
About
share again.
okay. There.
Okay, perfect.
Can you
My
hear?
name is Ayana Pita. I am from.
I did a record about my presentation. Can you see?
Yes.
Yeah. Go, please go.
Okay. Okay, my name is Ayana Pita. I am from Venezuela. Currently living in Buenos Aires, Argentina. I am a civil engineer and I'm completing a master's degree in sanitary engineering at the University of Buenos Aires, Argentina. And I'm an active member of YPM Venezuela. I would like to present my work titled Water Quality Modeling of Paraná River between the Yacyretá Dam and its junction with Paraguay River. The following work shows the result of the study of the dispersion capacity of 6 hypothetical pollutants and the variation of the concentration along a section of the Paraná River between the Yacyretá Dam and the confluence with the Paraguay River, making use of the software water quality module in HECRAS. First, I'm going to describe the methods. Figure 1 here shows the Yacyretá Dam and downstream the confluence with the Paraná River and the Paraguay River. The data to model in HECRAS was obtained from a practical case seen in the subject math models from the specialization course Sanitary Engineering of the University of Buenos Aires. Once the geometry and hydrodynamics had been loaded, it was necessary to load the quality parameters, concentrations, decay coefficients, and type of discharge. The tables number 1 and 2 show the characteristics of each pollutant under study. In table 1 here, you can see how I combined the conditions so that 6 different pollutants could be modeled. Table 2 shows how the concentration of the pollutant varies at the entry point, in this case, the Yacyretá Dam, for the 9 days of study. The results were that pollutants 2, 4, and 6, being non-conservative, have smaller curved areas than pollutant 1, 3, and 5, respectively. This is due to the fact that when having a decay rate K, the concentration decreases over time, while conservative are only diluted by dispersion. Punctual pollutants have graphs in Gaussian form, where the peaks move by reflection and decreases by diffusion. The peak concentration of the pollutant decreases along the river. In the case of the non-conservative pollutant, the area under the curve remains constant throughout the entire route. And in the case of the non-conservative, the area decreases according to the decay rate K. Figure 3 here shows the concentration along the section along the river section on days 5 and 7. Here, 5 and 7.
Venezuela.
5 and 7.
Currently living in Buenos Aires.
In the case of punctual pollutants shown in red and gray lines, the peak move, and it can also be confirmed as in the case of the non-conservative, the gray line, the area under the curve, that is the concentration, is less than that of the red line. This happens because the gray is non-conservative. In the case of day 9, only pollutant 2 is shown, which is constant and non-conservative, and it can be seen that its concentration at the confluence point is practically 0 on day 9, and it was diluted by 94%. This is the confluence point. Therefore, the conclusions are the following. The non-conservative pollutants has a decay rate K less than 0, and the concentration decreases over time. Conservative pollutants are only diluted by dispersion. In punctual pollutants, the peak moves by advection and decreases by diffusion. The HEC-RAS water quality model allows researchers to create simulations which represent different future scenarios found in nature in order to establish the most probable behavior of water bodies. It is also possible to study different conditions by modifying the input data. CNIT allows evaluating the variation in the concentration of a pollutant versus space and time. And finally, I would like to thank to all listeners for the time. It was a pleasure to be a part of this event. Thank you.
Okay. Thank you, Diana. So our next presenter is Byung-Kook Kim, and his presentation is about a method for simulation of reactive salt transport in natural rivers. So please.
Do you hear me, sir? Do you hear me?
Yeah, please.
Yeah. Okay, let's get started. Good to see you, chairs, hosts, and colleagues. This is Byung Kim from Seoul National University, South Korea. I'm going to presenting the advanced model for the chemical contaminant transport in river. The solute transport models have been studied for like 30 years or more, but most of them still assume that all the solute is conservative, but it's not true. Recently, not recently, in the past 20 years, there have been lots of attempts to consider chemicals' decayability in river. The simplest way was containing the first order decay term in the model. As Mr. Carlo mentioned to me, thank you for your comments. And Mrs. Diane Pita present as well. Here, the thing is the decay parameter. Some of study use the actual organic chemical as a tracer, and some of study use the smart tracer to estimate the first order decay parameter, but they still have fatal disadvantage from the optimization. As you guys know, the optimized decay parameter has a local problem and cannot be covered various range of toxic chemicals like phenol, benzene, or something. In this study, based on the transient storage model, which is the most popular one-dimensional model, we proposed the theoretical and empirical method to estimate the decay parameters reflecting volatilization and biodegradation. First of all, for the volatilization, we employed the two-phase theory. This theory says that there are two-phase boundary layer on the interface between water body and air, and the mass transfer is caused by a concentration gradient and diffusivity. Based on this concept, we derive the equation to obtain the volatilization rate corresponding to the chemical's volatility. This estimate rate was validated with the other volatilization model as well. Second, for the biodegradation, we employed the BioWin model developed by US EPA, which is reliable estimator for the biochemical half-life. The numerical model for this advanced governing equation was constructed, and the simulation was carried out based on the tracer test in Gam Creek, the creek in South Korea. The toluene, phenol, and sulfuric acid were set as subject chemicals. In the figure 1, We can see the considerable difference by different type of chemical. At about 5 kilometers downstream from injection, the toluene lost 57% of its initial mass. Even though these decay parameters were estimated based on the actual phenomenon, the resulting cannot be 100% reliable. To evaluate how the decay parameter function in the transport model, we did the sensitivity analysis. The degree of decay is not only dependent on the decay parameter, but also flow characteristic like flow velocity or something. So we used the Denkola number to normalize the decay parameter from the flow properties as shown in the figure 2. To sum up, the results of this study supports the necessity of consideration of chemicals' reacting property in the transport model. And we also suggest the significant reason to evaluate the first order decay parameter using Denkola number. Let's bring us to the end of my presentation. Thank you.
Thank you, Kim. And now we have with us also Sadoi Karki. So we are our last presentation. Sadoi Karki with the presentation about how good are 2D morphodynamic models in reproducing bed morphology of meandering channels, a comparative analysis of 3 models. Please, Sadoi.
Okay. Yeah. Hello. Yeah. Yeah. Are everyone able to see my presentation?
Yeah. Please.
Okay. Thank you very much. I am Saroj Karki from Nepal. And the topic of my presentation today is how good are 2D morphodynamic models in reproducing the bed morphology of meandering channels. And here I try to compare the strength and limitations of three widely used 2D morphodynamic models. Basically, what I did is I choose one experimental case that has been already performed from the available literatures, and for that experimental case, I applied 3 different models, and the models that I applied are Telemac 2D model, and NACE 2DS model, and the CCHE 2D model. Basically, the Telemac 2D model, it solves the shallow water equations using the finite element approach in an unstructured computational mesh. And the sediment transport model, CCIF, and the hydrodynamic model Telemac 2D are internally coupled. Whereas in NACE 2DS, it is also a 2D model for simulating unsteady horizontal flow, sediment transport, and morphological changes in bed and banks. And but it is based on the curvilinear coordinates and the structured mesh. Similarly, CCHE 2D is also a depth averaged 2D model, and it is also based on the quadrilateral mesh or the structured mesh. So the hydraulic condition of my experimental case from the literature was the 9.8 liter per second of constant inflow discharge was supplied, and the downstream depth was set at 5 centimeter, which is the average flow depth for the given flow and the channel geometrical conditions. And the channel was basically a sine generated meandering channel of the deflection angle 70 degree, and the sediment that was placed in the bed was non-uniform sediment with D50 of 0.65 mm, and the bed slope was 1:250 along the center line. So as you can see from the figure that the figure A is the experimental case, and whereas figure B is for the NACE 2DS simulation results for the NACE 2DS, and C is for the Telemac 2D, and D is for the CCHE 2D models. And what we found is that in general, all the 2D models that were applied in this study they were able to capture the bed morphological process as a whole in general, like the scour along the outer banks and the formation of the point bars along the convex bend. But what was found that the particular bed features were captured by different models by different accuracy. So if we see that the NACE 2DS model, the scour along the outer bank was better captured by the NACE 2DS model, whereas the formation of the point bar along the convex bend that was better captured by the CCHE 2D models. And whereas the the performance of the Telemac 2D model was in between NACE 2DH and CCHE 2D model. And similarly, in Telemac 2D model, the scour depth along the outer banks was more underestimated compared to the other two models. So basically, what it can be concluded that each model in general is capable of reproducing the meander bed morphology, but there exists differences in capturing particular bed features like point bar or the outer bank square. So for the analysis is needed under different flow conditions to get more detailed insights of the various aspects of the 2D morphodynamic models. That's it for my presentation. Thank you very much.
Okay. Thank you, Saroy. So we are at the end of our presentations. And now we have time for discussion. Please, Michael.
Yeah, well, I have one question from the audience regarding the last presentation. So, Saroy, you say that the differences between the models are mostly due to the different in the model itself. But have you tried to compare models having the same grid, the same computational grid, or how? Well, the other question is, what is the rationale for choosing these models and to compare those models?
The grid size that I considered is in general close to each other. I considered around 4 centimeter. But since the two models like NACE 2DH and the CCHE 2D model were structured grid models with quadrilateral mesh, whereas the Telemac 2D model, it is unstructured with triangular meshes. So, but in general, I try to make the mesh size more or less the length of each mesh around 4 centimeter in all the 3 cases. And the second question is basically there are like lots of 2D models for simulating the bed morphology for bed morphology of natural rivers, but like the model that I choose is like they have these 3 models are they are among the models which are widely used. But I can't confirm that only these are the widely used. There are other models also which can be incorporated in future. But currently, to my knowledge, these are also one of the popular models. So that's why I choose these 3 models.
Okay, thank you. The same for you. How do you compare only the computation of one steady flow for all the 3 models? Or have you planned to perform different analysis also regarding the hydrology?
Yeah, for the first step, I only assumed one particular flow, one steady uniform flow. But I plan to perform under different flow conditions. For like this is 9.8, and I will try for like let's say 6 liter per second. And also I will try to incorporate with the unsteady flow with some particular hydrograph. So that is my future plan.
Because yeah, as you saw, the choose of the discharge that you choose affect the sediment transport. So maybe changing the discharge, you have a different path and you have different results in terms of model performances.
Yeah, yeah. The experimental case that I chose for this study is taken from the Da Silva et al. 2008 one paper. I found that, and in that paper they have performed for 3 or 4 different flow conditions. Like the maximum is like 9.8 liter per second, and they have like 6 and 3 liter per second also. So I will try to incorporate on the different flow condition and try to see how the performance of the model changes with different flow conditions.
Okay, thank you. Well, another question, this time for Diana. What were the obstacles that you found working with HECRAS and evaluating the dispersion capacity of a section? So, yeah, how you deal with simulating dispersion with HECRAS?
In this case, we don't have problem, but the principal problem with a graph is that you can do the model in 3D. That's the principal problem.
Okay. So now I have a question for Rossella. So you show that the discharge of the Power River and the wind are the main drivers of the plume. Have you computed, or were you accounted also for the tide, or?
No, we didn't account for the tide, just wind and river discharge, but we can deepen the analysis considering also the general circulation and the structure of the general circulation in Northern Adriatic Sea, and also tide currents, yes. But for now, just wind and discharge.
Thank you. There's no more question from the audience. So, Angelo, if you have something.
Yeah, I just another small question for Saroy about the last presentation, because in my opinion, the main problem when you want to simulate a meandering channel in which you have a strongly 3D flow with a 2D depth integrated model is some trick for reproducing the helicoidal flow. In Telemac 2D, I know you have some correction for the helicoidal flow. Do you use this correction, and what do you do in other models?
Yeah, thank you for your question. Yeah, actually, in all of the 3 models, they have the secondary flow correction factor available. So in Telemac 2D also they have the secondary 2D correction factor incorporated in their model. So in all of the 3 models, I used the secondary flow correction before. I mean, while performing the simulation. But the approach might be different in each of the models. The correction approach may be different, but whatever the available option there was in the model for correcting the secondary flow or the helical flow, I have incorporated that.
And is it important for the results? Which differences you find with and without the corrections? I mean.
Yeah, sorry. Actually, I did not since my study is on the meandering channels. So currently, I did not do without secondary flow correction. So I only did the cases with correction. So I have not checked for the cases without correction.
Yep. Okay. Any questions? Any other questions from the audience?
So yeah, Jose, go ahead with your question.
Hello, I would like to know what is your opinion about when you are doing some kind of 2D models, how many mesh sizes are you testing? I will know the ideas, the feelings of the different presentation, the expositor during this session, to know if they are considering only one mesh size, different type of mesh sizes, if they prefer rectangular or triangular elements per their studies.
Yeah, okay. Yeah, like I said previously also, the mesh size in each of the models, like the NES 2DH and the CCHE 2D models, they are like quadrilateral meshes, whereas the Telemac 2D is the triangular meshes. However, I tried to make the mesh length of the mesh in each of the models close to 4 centimeter in all of the 3 models, and the benefit with the unstructured mesh is like while you perform the simulation with some structures or some natural rivers where the shape is not exactly like meandering or not exactly one particular shape. So in that case, triangular meshes are quite easy to incorporate those shapes or like some structures, let's say some groins. But whereas in the quadrilateral meshes, when we try to incorporate some structures or try to incorporate the particular shape of the river, that might be some difficulty, not as smooth as the unstructured mesh for the Telemac, like the Telemac 2D models. And like you said, the different the selection of the mesh size might also affect our model results. But currently, I did not check the sensitivity of the mesh size. I only performed with one mesh size. Like this is just the initial phase, and like I will try to perform check the sensitivity of different mesh size also. How the performance will be affected by different mesh size. Yeah, there have been some studies like in Telemac 2D, they have checked the sensitivity of the mesh sizes. So I will also try to incorporate that in near future as far as possible.
Okay. Other questions?
Yeah, still to Saroy, have you tried to relate to something the changes observed between the results of the 3 models, or well, they are different models which are based on different hypotheses. So what could be the measure driver of changes of? Have you, yeah, from your analysis, can you say somehow what is the best model to simulate your case studies, and why is this the best model?
Yeah, in my opinion, like I found NES 2DH much like the performance of the NES 2DH is quite it good compared to the experimental cases. Like it closely matched with the experimental cases for the NES 2DH, and well we change the secondary flow parameters or some sediment related parameters. It is more easy to get to the actual experimental results. Like for the Telemac 2D and CCHE 2D model, like even the sensitivity was quite less. Like if I change some parameters, and if I try to like achieve the experimental results in the simulation, that was quite difficult. Like even if I changed some parameters, the change in the results was not much as compared to the Nest2DS model, where if I change some parameters in the Nest2DS model, I could get close to the experimental results more easily. So the sensitivity of Nest2DS was to the change in parameters related to sediment transport was quite good. So that can be like more easier or helpful if we try to simulate for the real field cases.
Hello, Sarov.
Yes.
Okay, you're being particularly attacked with questions. I'm going to attack you with another one.
Sure.
So more generally in your study, my question is, to what can you attribute the differences in the results you obtain with the 3 codes that you're using?
Sorry, can you repeat once?
So to what you can attribute the differences in the results that you're seeing with the 3 codes that you're using? You made this study with 3 different codes, you had 3 different results. But from the study itself, or what you said in the presentation, is not clear to me whether you can attribute those differences.
Yeah, okay. So yeah, basically like each of these 3 models, like they are built on like different approaches, and also the approach in the sediment transport or the approach in the mesh, or like some are based on the Cartesian grid or on structured grids, and some are based on the like the quadrilateral grids and the curvilinear grids like Nest2DS. And so that might be one of the factor for differences in the performance, like the size of the mesh, or the and the another might be the like how the sediment transport is coupled between the hydrodynamic and the sediment transport model. Like in Telemach 2D, there is internally coupled. So first we get the hydrodynamic variables, and that are fed for each time step, and that will give the change in the bed morphology. So each of the models are based on different approaches. So that might be one of the factor for that one. And other things like the experimental cases and the simulation cases, I try to keep the parameters and the sediment transport like the formula, like in all cases I try to incorporate the Mayer-Pair MPM, Mayer-Peter-Muller formula for the transport of the bed load. So the differences might be the approach of the modeling, the sediment transport approach, and the grid, the generation of the grid.
Okay, from that perspective, that's as you have might notice, then probably a suggestion for your study would be to first perform a grid sensitivity analysis on each of the codes that you're using in order to discard this discussion of having different grids or different grid sensitivities or sensitivity to the grid on the solution, given the fact, because what I see right now is just basically, okay, you run 3 simulations, but you have too many things that could be affecting your solution. You could say also you could attribute the differences with the results of Ferreira just to the fact that you are using the Meyer-Peter-Muller, and probably the Meyer-Peter-Muller is not the correct model to study bed load on that system. You attribute it. The thing is a dangerous path to attribute it to the code, meaning saying that is because finite elements or because you are using finite differences with curvilinear grids. Let's say is the easy way out. So my suggestion would be first to do a grid sensitivity analysis, build 4, 5, 6 grids,
with different refinements, try to see if you get convergence on the grids. Then from those, starting from those grids in which you don't see changes,
Yes.
then from there you can start making a conclusion regarding the performance of the simulation parameters. But from me, it seems that at this stage you cannot take any sensible conclusion about what you have right now.
Yeah, you are correct. Like this is just the the first step, and like further analysis is detailed analysis, like based on the grid sensitivity and different flow conditions might be necessary before we reach to a general conclusion. Yeah, I agree on that.
Okay, thanks.
Yes, thank you very much.
Okay, if no one question, I have one for Rafael Belguillos. Yes.
Yeah, tell me.
I really appreciate your presentation. I really appreciate all presentations. Thank you to all, because the good level of presentations. But for Rafael, I appreciate also the presentation of this open source code. I go on the website in order to check it, and I tried it. It is very interesting. I just two curiosity. The first one is about the kind of geometry you can treat with this code, because I can see some simple example about simple geometry, but can you handle with irregular geometry like natural geometry with your code? And the second question is your opinion about this kind of correction for taking into account non-hydrostatic behavior in the case of irregular geometry, because I have an opinion about it, but I will say later. Please, Rafael.
Yeah. Okay. Well, the software platform, the GUI in that is presented in the poster, only for the moment only includes the 4 applications that are shown in the poster. But the BAM model can be applied to other more complex geometries, as you said. And for this reason, the MATLAB scripts of the model are also provided in the along with the paper of by Gamero et al. Are provided, are freely available too. So if you are interested in modeling different, more complex geometries, I encourage you to use the MATLAB script that have been provided. And anyway, the software platform can be adapted to include other tests. I have only some 4 simple applications just for the purpose of highlighting some potential application of the GUI, but the BAM model is obviously applicable to other more complex geometries. Actually, tomorrow at I don't know, I think is in the first session, there will be some more application of the BAM model.
Okay. The reason of my question were about the fact that my question were connected also to the one to discussion we had with Saroy. This because my opinion when you use these complex models is that when you are in a complex problem in a natural geometry, in many cases the uncertainties you have in representation of the geometry, in representation, in calibration of parameters, usually can hide these other effects. But it's just my opinion, and I really appreciate this kind of model. Any other questions? Some other doubts? If no one, I have another one. So, I have one for Diana Pita about her presentation on the dispersion in the Paraná River. Because I see your conclusion about the fact that you have concentration profiles that are Gaussian at each time. What about the geometry of your river? I mean, how irregular is it? No, the microphone.
The principal objective of my work was show the difference between the six hypothetical pollutants. That was the principal objective of my work. But the geometry, I take the hydrodynamics from the specialization of the course in my master's degree at the University of Buenos Aires. I only use the model of HECRAS to evaluate the difference between the pollutants. And I combined 6 different conditions when I use a constant, punctual, conservative, and non-conservative, all variable.
Okay. Any other questions? So, if we have no more questions, we can close our session. Michael?
There's no more question from the audience.
No more questions? So we have just to thank you all for your participation in this session, and I repeat my invitation in join the Fluvial Hydraulics Committee. So, thank you to all.
Thank you very much, Angelo.
Bye.
Thank you very much for everything.
Thank you.
Thank you, Jose, too.
Okay. Next session will start in 15 minutes. So you have some time to do a break, and we'll see in the other new parallel sessions, urban drainage, or the other is, let me check in the program. In this room, we are going to continue with urban drainage, and in room number 1, you have climate change adaptation. So we will see in a few minutes. Thanks.
Okay, see you.